Hello everyone, welcome back. We're going to be continuing with the physics Matric questions. We are on grade 12, unit 4, Electrostatics. Let's move to the question. So question number 21 states that, suppose that 3-point charges are placed along a straight line and the electrostatic force exerted on the middle charge is 0. What can we conclude about the charges? The choices are, the signs of the 3 charges should be the same. The middle charge should be placed at the center between the 2 charges. The charges at the ends must have the same sign. The charge at the middle and at the left end should have the same sign. So before going into the choices, let's have a general understanding of what is meant by charges. So charges are one of two. They're either positive or negative. And these positive or negative charges have electric fields surrounding them, acting in a certain direction. So for positive charges, these electric fields are acting in the outwards direction, away from the center. And for negative charges, these electric fields are acting towards the center of the charge. So when these two types of charges interact, or when they're near each other, different things happen, depending on if the charges are opposite or if they are the same. So for the situation when the charges are opposite, what happens is that they are attracted to each other, just like the famous saying, opposites attract. It comes from here. So opposite charges attract, meaning that the electric fields leave the positive charges and enter the negative charges, causing the attraction force. Alternatively, if the charges are like, meaning if they are positive, or negative, these two pairs of charges will repel each other because the electric fields are acting against each other. The positive electric fields are going out, so they will clash with each other like so. And similarly, the negative electric fields are acting inwards and they will also clash with each other like so. So they will in fact repel each other. So this question is talking about 3-point charges. Let's move this screen down a bit, keeping that in mind. So if you have 3-point charges like so, let's say we have one charge over here, one charge over here, and one charge over here. If you have 3-point charges, it's asking what is the situation or what can be concluded about these 3 charges if the electrostatic force acting on the central charge is 0. So let's first denote the 3 charges as Q1, Q2, and Q3. And you have to know that there is an electrostatic force acting between Q1 and Q2, and there's an electrostatic force acting between Q2 and Q3. Let's call this first force F1 and the second force F2. The general formula for electrostatic force states that F1 is equal to some constant K times Q1 times Q2 over R squared, and F2, similarly, will be K, Q2 and Q3 over R squared. Let's call this R1 and R2, and let's define it as the distance between the charges. This is R1, and this is R2. So the question states that what must be done for these two forces to be equal and opposite. That is the only way that the force experienced by the central charge can be 0. So let's look through the choices, keeping in mind what we mentioned earlier about charges, that like charges repel and opposite charges attract. Let's go through the choices. The first choice says that the signs of the 3 charges should be the same, saying that all 3 charges should have the same sign, which means if this has to be negative, this has to be negative, this has to be negative, or all 3 have to be positive, have to be positive, have to be positive. That's the only way that the central charge can experience 0 force. Well, that does make sense if you consider that Q1 will repel Q2, or it'll push Q2 away. Similarly, Q3 will push Q3 away. That does work, that does make sense. But if the central charge is negative, this also can still work, because Q1 will pull Q2 towards it, and Q3 will pull Q2 towards it, so you could still have a 0 force. So it isn't necessary for all 3 to be the same charge. The second choice says that the middle charge should be placed at the center of the 2 charges. Well, yes, that could help a situation to make the 2 forces equal, but that's not exactly necessary. Let's say, for example, let's try to move Q2 a little bit. Let's move Q2 somewhere over here. So if we move Q2 somewhere over here, That means the distance r will be shifted like so. R1 will be shifted here and R2 will be shifted here. So we can see that, forget the charges, forget if they're negative or positive, that's not our concern. The position is concerned. So we can see here that R1 has decreased. But if we increase Q1 instead, then we will be able to compensate it. Here R2 has increased, but if we decrease Q3, it's possible for these two forces to be equal. So it's not exactly necessary for the central charge to actually be in the center. Let's look at the third situation. The charges at the ends must have the same sign. This seems to make the most sense. If we see that if this is positive and this is positive, meaning that they have the same sign, no matter what the central charge is, if the central charge is positive, then they'll both repel, right? But if the central charge is negative, then they'll both attract. Similarly, if we think of the situation, let's say in either end we have the same charge, we have a negative charge at either end, like so. If the central charge is negative, again, they will both repel. But if the central charge is positive, then they'll both attract. So it doesn't really matter what the charge of the center is. All that's really concerning is that either end the charges should be the same. Let's look at choice D just to be sure. It says that the charge at the middle and the left end should have the same sign. Well, that's saying that the charge at the middle, let's make this negative, and at the left end is also negative. Okay, if they are of all three the same sign, that could work. They would both repel each other, like so. They'd both repel each other, like so. But let's say that the charge on the right end is in fact, positive. Well, what'll happen then to the forces of attraction? Well, Q3 will pull Q2 towards it, and Q1 will push Q2 away from it. There is no way that the addition of these two forces could add up to be zero because they're acting in the same direction. So it doesn't matter what the central charge is. What does matter is the charges at either end must be the same, be it positive or be it negative. So that concludes that our best choice is choice C, the charges at the ends must have the same sign. And that's it for this question. Moving on to the next question. Question 22 states that a capacitor of 12 microfarad capacitance can be fully charged after it is connected between a potential difference of 9 volts. How much electrical energy is used in charging the capacitor? This question is about a capacitor. This capacitor is an electronic device that is famously known for its ability to store charge. That is the key purpose and use of a capacitor. How does it do it? Well, capacitor is symbolized like so. And if you connect this capacitor to some sort of cell or some sort of battery, where you have one side as negative and one side as positive, so what happens is that the side of the capacitor connected to the negative end becomes charged with electrons. These electrons will keep building up on this negative side until the potential difference of whatever this battery has is reached. Once that potential difference is reached, then the charges will be discharged across to the other plate and flow back to the positive terminal of the cell, completing the circuit. So until that voltage is reached, however, charge will be stored in the capacitor. So capacitance is the ability of a capacitor to store charge per voltage. So the formula for capacitance, C, is the ability to store charge per voltage. So when we look at the question, we are given that the capacitance of a certain capacitor, the capacitance is 12 microfarad. Farad is the unit of capacitance. And we're also given that it is connected to a voltage of 9 volts. The question asks, what is the energy required to charge the capacitor? Again, this energy that is used to charge the capacitor will later be discharged by the capacitor itself. So the solution to this question is to find the energy of this capacitor. The formula is given as half QV. Now we're not given Q, but we can use this formula. We can use this formula over here in order to substitute. So we know that C is equal to Q over V. And rearranging this, we can get that Q is equal to C times V. So putting this into this formula over here, we get that energy is equal to half CV squared. Let me shift this up just a bit. And we can now calculate that energy is equal to half the capacitance, which is 12 microfarad, multiplied by the voltage, 9 volt squared. This will be equal to 486 microjoules. If we want to write this in scientific notation, this will be 486 times 10 to the power of minus 6 joules, because micro is 10 to the power of minus 6. And this can be further simplified to 4.86 times 10 to the power of minus 4 joules, simply by shifting the decimal 2 spaces. So that will be our final answer, 4.86 times 10 to the power of minus 4 joules. And if we look at our choices, that is in fact choice A, 4.86 times 10 to the power of minus 4 joules. If you use the formula correctly and put in the correct values, this is the only answer that you can get. And that's it.